Hi, this is Professor Cummings, and I have another example for a rotational analysis. And this is, again, still part of that series for this semester. And it's a little simpler problem than we've looked at in the last time. This one is just a disk. It's got a radius of 0.4 meters and a point of interest P. And so let's read up on what they're asking. The disk starts from rest and is given an angular acceleration, and it's expressed as a function of 2t squared radians per second squared, where t is in seconds. Now determine the angular velocity of the disk and its angular displacement when t is 4 seconds. So that one is a little bit easier, not as many, doesn't mate to anything, doesn't share a velocity or a point of rotation. So we're just asking everything on this one rigid body. But there are a few things that I want you to take into account. Now let me go ahead and make this into a pen. First, the disk starts from rest. It's given an angular acceleration expressed as a function. Determine the angular velocity of the disk and its angular displacement at a very specific time. So it's a few things that we know that are going to tell us a bit about the problem, helping us to go into a particular direction. So let's see. So we've been given the angular acceleration as a function, 2t squared radians per second squared. We've got a radius of 0.4 meters and a window of time of 4 seconds. And we're just looking for the angular velocity and the angular displacement. And so when you think about this problem, I want you to consider, this sort of imagery. So you move through theta as your rotational displacement, and also that we're relating all this through the radius of the rotation, radius of the object, the rigid body that's going through its rotation. So if you look at this from this point, our angular acceleration and angular velocity are going to stay the same, but as you move inward and outward, change the radius, that's what ultimately changes. Now let's see, we also have a few relationships that are going to serve us, so let's go through some thought processes that are going to help us. Here we have the acceleration is expressed as a function. Okay, so we've given that, and the angular velocity and angular displacement can both be derived from that original function, right? So the angular velocity, is going to be a definite integral starting from rest 0 to whatever final velocity it gets at over that window of time, and the acceleration, which is going to be expressed as a function with respect to time between that same window, 0 to 4 seconds. Now, once we have this solved, we can now start looking at the displacement from 0 to theta. So we know that's an unknown, but we will have a window of time again that we're looking at 4 seconds. So let's see here. So let's just start off looking at our angular velocity. Like I said, so you got a window between 0 and 4 seconds, and we want to know what the velocity is, the angular velocity, at the end of that 4 seconds. And we do have our acceleration expressed as a function of 2t squared radians per second squared. So if we replace that function and we integrate that as a definite integral, and again, I'm just looking at the right side of the equation. The 2 comes outside the equation, or outside of the infinite sum. Add 1 to the exponent, making that a 3, and divide by the new exponent, and that leaves you 2/3 t cubed from 0 to whatever that final time is. On the left side of the equation, the integral of d omega will just get you omega minus omega, and that goes from omega to 0, because it was starting from rest. And from there, this goes to 0. That's obviously 0. So what you end up with is a function there. Then you can plug in the t of 4 seconds, and you end up with this function. And at 4 seconds, you end up with 42.67 radians per second. So that is how fast it's going at the end of 4 seconds. So there we have that angular velocity at the end of 4 seconds. But now let's figure out how much displacement it's going to take. And again, we have a function here of our angular velocity that we can plug in. Again, those are just a separable differential equation. That's the relationship between displacement and velocity, and displacement and acceleration like the last one. And again, we have this window of time, 0 to 4 seconds, and this 0 starting from rest to some displacement. And we'll go ahead and solve that one. On the left side of the equation, you have the final displacement minus the original, which is going to be 0. And on the right side of the equation, since this is so simple, add 1 to the exponent, the omega squared divided by the new exponent. So 1/2 omega squared, starting from 0 and going to 4 seconds. So that's the function. And sorry, I should have said what the function is. So adding 3 to this, excuse me, adding that to, it'll be 4 divided by the new exponent, which would be 2 over 4. 2 over 4 times 3, excuse me. And that'll give you 12. So omega minus 0, again, starting from rest, and time intervals at 0. So now you've got a new function of theta equal to 1/6 of t to the 4th. And we have a window of 4 seconds. And you end up with 42.67 radians. So that's how much it rotated about. So again, so that was a little bit more straightforward. And this is Professor Cummings. Go ahead and like the video. Subscribe to the channel if you're not subscribed. And if you have any questions or any sort of feedback or any information, go ahead and leave it in the comment section. Until then, I'll talk to you in our next video.